Comparison instructions.
Comparison instructions. In the most fundamental terms, you could say that the XIC, or the instruction that I refer to as true if on, and the XIO, which I refer to as true if off, that these instructions are comparison instructions, that they are the binary equivalent to the equal instruction, the EQU equal instruction. The XIC would be true if the bit in memory that it addresses is equal to 1. The XIO would be true if the bit in memory that it addresses is equal to 0. It is unnecessary to understand the depths of the instruction set to be a successful PLC PAC programmer. However, a cognizance of the instructions at a binary level, a level closer to the architecture of the firmware, will serve you well both when you're troubleshooting and when you're trying to write simplistic code that is easily readable by your customers. Your programming solutions will come quicker and result in much more efficient code. Temper this with an understanding of your readers, those that will read your code later, most of which will be troubleshooting a manufacturing system by reading your code. And you will be a respected member of the PLC programming community. Too many programmers consider the terminal destination of their project to be when the machine runs properly, giving no thought to how the machine is going to be maintained. Writing PLC code is not like writing an app for a mobile device or creating a web page using HTML, Java, other languages, because the users of the mobile app or the web page will probably never see the code unless they accidentally click on Inspect Element. Whereas PLC code, almost without exception, will always be read by the customer in the course of troubleshooting the system. If you do not write your PLC programs to be easily led, easily read, easily analyzed, you're making a big mistake. That is why ladder logic diagrams still are the most popular form of code for PLCs. You can use all four languages. I use all four languages, but primarily I use ladder logic diagrams for the bulk of the code. I use structured text for convoluted math subroutines, and I use function block diagrams for temperature control, process control elements of a process. A comparison instruction is a mathematical statement or equation that is either true or false, but never both. 1 equals 1 is true, or 1 equals 0 is false at the digital or the binary level. The first instruction that we're going to look at on the screen in front of you is the equal to instruction. 1 equals 1 and 0 equals 0 are true, but 1 equals 0 and 0 equal 1 are false at the digital or binary level. Because this is at a larger value level, meaning that you can use this instruction with everything but Boolean. You cannot use Boolean tags here for source A and source B. And of course there would be no point of using constants for both source A and source B, although you can use a constant for one of the two. If you're going to use constants, I would stick to B and let A be the variable and B be the constant. I had you open up any project or create a new one. You need your I/O modules. You need your I/O module defined tags. I had you add this single rung of logic that you see. Define all tags as program tags. And at this point, it really doesn't matter whether you make them program tags or controller tags, because the logic will still function perfectly fine. The point in specifying the scope, program tags, is so you get in the habit of always considering the scope of the tag when you create it. In the real world, you are comparing two values of equality or inequality. One of them is your benchmark and the other is of interest. I always tend to think of source B as the benchmark because normally when you are looking for something of equality, you already have in mind what your benchmark is or what your value that you are keeping things to, or you want to check equal to. The one that you're looking for, an equality, is compared to the one that you already have. You typically compare what you see to what you have, not what you have to what you see. That's just a matter of semantics. In this case, you are only interested in the instance where some other value is equal to your value. I have it exactly the opposite of what I just spoke for source A and source B, because it really doesn't matter, and I did that on purpose. It doesn't matter which you make your value and which you make some other value. They're just two values, two tags. You have picked a value and you are looking for an exact and unequivocal equality. Never lose sight of the fact that all of these values are in reality binary bit memory locations 8 or more. Single integers, integers, double integers, etc. And I ask you if this value were true, or I should say if this rung is true. Now, we're not in the online mode, but you should be able to look at it and ask yourself, is 0 equal to 0? And that is the only condition in this rung, therefore this rung would be true. Just to verify that, now you see that we're online. I put it in the online run mode. And by the way, I'm using an L35E Compact Logix processor simply because it's much faster for upload, download, online edits, etc. Just to shorten the video time. So the answer to the very first question in this section is yes. The rung is true. Had you saved your project, download, go online in the run mode, if A equals B, then B equals A. Is that a true statement? Of course it is. If A equals B, then B does equal A. I had you edit your logic. I had you edit your logic to add another equal instruction and then reverse the order of source A and source B, just to show you that the rung is still true. And of course, this bit would not be on if both of these were not true. So the logic here reads, if this is true and this is true, then turn on that bit. I then had you delete the second equal instruction. Double click, select it, hit delete, finalize all edits. And then I had you change source B to 5 to demonstrate the false state. Although you're comparing two double integers whose value can range from a minus 2 billion and some to plus 2 billion and some, the result or conclusion of a rung state out of the equal instruction, it's either true or false. Whether it's large values, small values, it's either true or false. Then I had you enter a value of 5 for source A, and of course now the equal instruction is true. The rung condition out of the equal instruction is true, and therefore the true aliased output, the light on your digital field device simulator, is on. Out of 4,294,967,296 possible values for source B, one of them is equal to your value, no matter what the value is. I had you add a second rung with a indicator on your digital field device simulator that energizes when you have a false rung condition out. That's not necessary in ordinary logic, but if you look at your digital field device simulator, if I change one of these values, this output goes off and this output goes on. Does this additional rung alter the state of the first rung? No, it does not. You could say that if the equal is not true, then by reason it must be false. However, with a PLC PAC, you have to have an action against a memory location for both. And in this case, we have, if the rung out is true, then we turn on that output. But if it's not true, then we do something else. So we have a true and a false state reaction in our outputs. If you want to use both conclusions and other rungs of your logic or control two field devices with both true and false, the comparison instructions are conditions only. Never do they alter values in memory locations. They are not actions. All of the comparison instructions are either true or false, and they have no effect whatsoever on any memory locations. I had to try a few values for source A and source B, until you were satisfied with the behavior of this instruction. I had you add the second rung to give you a action for both states of that equal instruction. Does this rung, the second rung, alter the state of the first rung? No. You could say that if the equal is not true, then by reason it must be false. However, with a PLC or a PAC, you have to have an action against a memory location for both. If, that is, you want to use both conclusions in other rungs of your logic or control two field devices with both the true state and the false state. The comparison instructions are conditions only. All comparison instructions are strictly conditions for the rung state. Never do comparison instructions alter the values in memory locations. They are not actions. I had you try a few values for source A and source B just to cement the behavior of this first of the comparison instructions, the equal instruction. Continuing from the previous project, the equal instruction, we had you add two more rungs of logic matching the first two, but with the not equal instruction and a rung condition true out to the not equal true, and the not equal true if off to control the not equal false. So now we have two instructions, both using the exact same two values, your value and some other value, so you can easily compare the behavior of these two instructions, the equal and the not equal, based on the four outputs on your digital field device simulator. Let us say that if you did not like the aliases for the tags that you used in the first two rungs of the equal instruction, that if you want to edit them, and that was part of the lab, I had you go up, right click, edit. Remember, you're not creating a new tag, you're editing an existing tag. And that's allowable online simply because you are not changing the structure of memory. You are simply pointing at a pointer and changing the text of the pointer that points to that particular memory address. In this case, local 10 data 0 and local 10 data 1. Go to false, edit, EQU underscore. So editing tag names you can do online without interrupting anything. Try changing the values of your value or some other value, or both. We'll just grab your value and type in 5. Now, the not equal is true and the equal is false because 5 is not equal to 0. This instruction compares 5 against 0 and it's true if they're equal. This compares the two and it's true if they're false, or if they're not equal. True if equal, true if not equal. Remember, I made the implication or implied that these are like the true if on, true if off, in a sense. Are the two instructions ever both true at the same time? No, definitely not. Are the two instructions ever both false at the same time? Absolutely not. Then I had you edit your rungs. I had you add an additional condition into rung 0. The rung 0 states if your value is equal to some other value and your value is not equal to yet another value, then you have a true state out. And obviously here, because it's not equal, the rung out, even though this is true, because 5 is not equal to 45,911, this is false. Therefore, because this is an and statement, this and this have to be true to get a true out, then the rung is false and the bit is off. If I change this to be true, then you see the rung is now true. How many different values can source B of the equal instruction be and the equal remain true? 0 different values. Right now source B is equal to source A. No other value for some other value will give you a true condition out from that equal instruction. Can yet another value be many different values and the not equal remain in the true out state, the true rung out state? Yes. You can have any value in here but 5, which basically gives you over 4 billion values you can have here and this is still going to be true. The next instruction that we covered was the greater than. We started out by saying open up any project that has the I/O configured and delete all of the logic and then all of the tags. The reason you have to delete all the logic first is you cannot delete tags from logic that's being used. We are in the run mode. Do not delete the I/O modules from the I/O configuration and consequently not the module-defined tags in the controller tag database. If you have any outputs on, go to the data table and keyboard them off to the off state. You see we do have one here that is on, and we cannot turn all of these off with the logic because two of these are always going to be true no matter what the values are. First thing we will do is we will go to the program mode, and here we can toggle the bits off because we're not executing the code. Then we can delete the rungs, finalize all edits, go to the program tags and select all of the tags and hit delete. Now you have to be in the edit tags tab to do that. But see, now we have a clean slate other than the name up here that's L35E underscore equal. But we're going to go back online and add more code. First thing we did in the next lab was have you add a rung of logic, and we had you do the same thing as before, delete everything and start from scratch with tags and logic. We have a rung here that will enable, disable a timer data type, so we have a value that's continually changing that we can use for our lab project. So if I push in input 0, if I push in input 0, the push button, you can see the timer runs. That just gives us a value to work with. I had you turn on the input 0, and let the timer time out. Does the accumulate stop when it reaches the preset? Yes. What is necessary to run the accumulate again from 0 to 10,000? Well, simply a false to true transition starts it over again. Now on my digital field device simulator, I didn't have to do the toggle switch. I just pushed the push button momentarily and get the change of state. That's the advantage of having at least one input on your simulator that can be maintained on, maintained off, or normally open or normally closed. Then I had you add a second rung of logic, and the second rung of logic is simply a input on your digital field device simulator, so you can easily just push the button and reset the timer and it starts over again. Or you can turn off the enable and it will reset. Either way. With both run enable and the restart timer switches on, so I turn on the enable, you can see it's timing up, then I flip on the restart. Is the timer data type accumulating? No. Why? Last man wins. Now here's where we're going to use the comparison instructions as a analysis tool. So we're kind of killing two birds with one stone here, or dotting two I's with one dot if you like that better. Flip the restart timer switch off and back on. Has the TON instruction that is addressing the instance of a timer data type anytime been enabled over the last several steps? Yes, it has. Flip the order of the two rungs. I'll do that in front of you. Every once in a while it doesn't hurt to do some of the actual code editing that I have in the manual. Remember, I did state that although in the first volume, beginner, I, for the most part, took you through step-by-step all editing. In this volume, Beginner Plus, we only do it occasionally. With both inputs on, which they are right now, restart timer and run enable, they're both on, is the timer timing. I gave you yes, no, or maybe for choices in the manual. Myself, I circled maybe, enabled for one scan, because remember, last man wins. So this resets the timer, this one enables it. So for one program scan, this instruction is enabled. But literally a microsecond later, you're at the end of the logic back to the beginning and it's reset again. So it is never true for 1/1000th of a second. So we still don't know if it's really timing or not. Then I had you add another rung. We'll put this at the end. Doesn't really matter. Well, actually it will for what I want to do. Do a true if on and a latch. So I'm going to grab any time, drag it down here, double click, dot, timer timing, enter, and then I'm going to label this captured. New tag, and we want main program scoped, a Boolean, finalize all edits. I'm going to toggle this back off. You're not going to see it go off though, but I did toggle it off from the keyboard to demonstrate that once this rung executes, the timer is enabled and the timer timing bit. So the timer timing bit latches this bit on to prove that the timer timing bit was on. Now you could put that timer timing bit in any, there you saw it change. Now remember that in a earlier lab, in the beginner manual, we demonstrated that the nature of the update of the I/O memory, which would be these 2 bits right here, is not synchronous with the code. So occasionally you're going to see this be false. If we were to drag this up here, I didn't do this in the manual, but I'm doing it now. Now I always have to clear that. Now you see that it's not, here it shows that this is true, but this shows that it's not on. There you see it just changed state, but you're not going to see this go on because you reset here and your timer timing bit is not going to come on until after this rung is executed. Because if I reset it here, then when the logic gets here on this same scan, this, even though this is true, this is reset, so the timer's not timing yet. And then when it comes back around, see, just depends on when the I/O is updated. So this is another situation where the fact that the I/O update is not synchronized with the continuous task, which is what we're running over here. The main task over here, as you can see, control organizer. See the little clockwise swirly? That means it's the continuous task. Okay, I'm going to move this back down here because that was not part of the lab. I don't want to muddy up the waters. My only goal here was to prove to you, so far, all that we know is that with both of these on, that we reset it and enable it, that the timer timing bit does come on with the enabled bit, and it shows it enabled, but you see no increase of the cumulative value. And again, I ask a question, would you say that the timer is timing? Yes, the timer timing bit is on. Is it accumulating? Maybe. I doubt it because our scan time, if we go to main program, properties, monitor, reset max, we're at 20 microseconds, at the most maybe a couple hundred microseconds. That's nowhere near 1/1000th of a second. And remember, the time base for these timer data type is 1 millisecond, 1/1000th of a second. So it's really not possible for it to accumulate. And keep in mind, every 20 microseconds, well, actually we would have to go up to the main task to look at the overall schedule. So we're actually, we'll hit reset there. The maximum scan time for the whole thing is roughly less than 2 milliseconds, but typically way less than 1 millisecond. So again, we wouldn't really have any time to accumulate anything, but we know that it's continually being enabled because this bit stays latched even when we turn it off. So the question, is it accumulating? Maybe. Now the actual final result, my answers that I selected now are based on observation, not on what I know. That's why I'm saying maybe. Just because we cannot see it does not mean that it is not happening faster than your screen refresh or the persistence of vision of your retina. How could we prove it one way or another? I had you add another rung, compare greater than. Now we're looking at any time dot ACC being greater than 0. So there we're using a constant. And then we have another bit that we want to latch, and that's captured 2. Now we know conclusively that the accumulate is not accumulating, otherwise capture 2 would be set to 1, correct? Absolutely. If the accumulate is greater than 0 at the end of the scan or at the beginning, one of these two bits, capture 2 or capture 3 would be on. And I did not add the capture 3 at the top. I'll do that right now. Move that up there. Actually, a better way to do this would be to take and right click, copy, paste. Of course, we want it at the very beginning. And we'll change this tag to 3. That's a new tag, so we define it. Finalize all edits. Now you see we have 3 captured bits. The only one that stays on is the timer timing bit. So we know the timer timing bit is coming on, but we can also see that our accumulate is not accumulating, whether at the end of the program scan or at the beginning. It's never greater than 0. So now you can truly answer that it is not accumulating. Do either of those 2 new bits latch? No, they don't. Is the timer accumulating? No. Now you may have answered no before. If your reasons for answering no were based on sound observation, then it would have been correct. If it was a guess, it was a good guess. If you are wondering where this is going, we are covering more than just the 2 instructions, less and greater than. We are using the instructions to analyze. So we're actually using the instructions in a logical function. And again, I had you go to the main task, properties, monitor. I had you reset the maximum. We really don't care about the maximum anyway. Ignoring the maximum scan times, what is the last scan time? I put in 80 microseconds. If you look at your decimal point, that would be 0.08 milliseconds, which is 80 microseconds. Even though you might see something a little bit different, don't use this value up there. This is really what we're looking at. Close the task properties and then add this logic after rung 0 and edit the current timer rung preset shown in the manual. This code is not something that you want to do as a habit, and that is putting loops inside of a routine. The code scans from top to bottom, left to right. If we look at rung 0, if the accumulate value of any timer data type is greater than 0, then we latch on this bit. And then in this next rung, this instruction right here is not really an instruction, it's just a marker. It's an identification of a spot in the code. There is no logical function for a label instruction. If the scan time stretcher is done, that would be this timer data type right here. If it's done, then we jump to flag 2 or marker 2. Marker 2 is down here, which means we skip rung 2 entirely if this timer's timed out and it's done. We jump to rung 3, we reset this timer data type, and if we have input 5 turned on, then we reset this timer. Then if the run enable is turned on, input 0, then we enable this timer. And then here we have our timer timing bit latched on. We come up and scan the rung again. Now if this timer is not done, then this rung is false and we execute rung 2, which jumps, if it's not done, it jumps back to label 1, which means for a preset of 400 thousandths of a second, which is 400 milliseconds, this processor will be stuck in a loop between rung 2, rung 1, rung 2, 1, 2, 1, 2, 1, 2, 1, until this timer is done. Then it skips to rung 3, resets this timer, and then comes back and does it again. So these 3 rungs right here, 1, 2, and 3, up to this point right here, this reset instruction, not the restart timer and the reset. But these 3 rungs right here are a scan time stretcher. Now remember that when we looked at our scan time for the main program, it was roughly 20 milliseconds. Now look, I'm sorry, 20 microseconds. Now look, so if we reset the max, you see it's 371, 372 milliseconds. Or you can do 372,000 microseconds. So we basically, or effectively, stretched our scan time. We did that for a reason. Ignoring the maximum scan times, what is the last scan time? Now this is for the program. Let's go to the main task and monitor it, because that's really more indicative. See, our max is 401. For all intents and purposes, you might as well say that the scan time is 400 milliseconds. Does this line up with a preset for the scan time stretcher? Yes, it does. Reduce the preset to 178 and check the time scan. I don't know if we can do, well, you have it pop behind 178, enter. We'll have to bring that back up. I can go look to see if it's behind. Yes, it is. You see 178 milliseconds. You see the behavior created by this scan time stretcher. Increase the preset to 500 and go back and check the scan time. Now before I could even get there to check it, look what happened up here. It faulted. That's what we wanted it to do. The task exceeded 500 milliseconds, and you'll see why that faulted this in a minute. Go up here to faulted. Go to faults. Don't clear faults. Always go to faults and look first before you clear it to see what it is. Task watchdog expired. May have been caused by an infinite loop, a complex program, or a higher priority task. In this case, we know what it was. It wasn't an infinite loop. It was just a loop that exceeded something. Go to Task, Properties, and go to the Configuration tab. And you see the watchdog is set at 500 milliseconds. This watchdog timer is there to protect the process that you're controlling from a situation where some sort of internal mistake or your mistake causes the program to execute for a length of time longer than what is appropriate. So it's set at 500 milliseconds, which means if this task goes for more than 500 milliseconds without starting over, you're going to fault the watchdog timer. Now the 500 millisecond setting is the standard, and really you should not have a program that's going longer than 500 milliseconds. Let's go back to faults. Go to faults. And notice that you were given a date and a time and a code, type and code for this fault. Increase it to the watchdog timer to 525. So we go back to main task, properties, configuration, and you set it to 525. Clear the faults. Put it back in the run mode. It is possible to get this processor to fault even though the watchdog timer is set at 525 milliseconds and your program is stretched out to 500 milliseconds. Right now it's not faulting, and it probably will not fault. However, there are certain functions that you can do that can bump the scan time a little longer. For instance, we'll just try one. We'll just pretend like we made an edit, and then we're going to finalize all edits. Nope, that didn't make it fault. So let's go look at main task, properties, monitor, reset, so we know what the maximum scan is. So it looks like it's 500 milliseconds. Say OK, and now we will put this in the program mode, this rung in the edit mode, and then finalize all edits. We're not going to get it to fault at 500. With the L31 processor, I was able to get it to fault on occasion with the watchdog timer set at 525 and a value of 500 in here. Now if we bump this up to 524, which is 1 millisecond under the watchdog timer, it may or may not fault. Occasionally there's a background task that takes just a little bit longer. So we'll try our other approach again, put it in the edit mode. There, that tripped it. So that little extra background task of editing something was enough to bump it above 525 milliseconds. So I'm going to put this back down to 400. I'm going to reset the configuration back to 500. We'll go to faults again just so you can see it's the same fault, watchdog fault. And then let's clear faults. Go back to the run mode. Now remember, we're doing comparison instructions. Put the restart timer switch in the off state and watch the accumulate of the anytime timer data type. What is it doing that is different than what you saw before you stretched out the scan time? We're going to have to reset it and watch it again. You see it's incrementing in 400 millisecond increments. And why is it doing that? Well, we stretched out the scan time, so the amount of time between when this rung is first false and executes this, jumps back to 1, and when it finally is done and jumps to 2, the time from this rung to this rung is 400 milliseconds. This rung is only being executed every 400 milliseconds. Therefore, the timer data type is incrementing in units of 400 milliseconds. Drop our scan time stretcher down to 200 milliseconds. Reset the timer data type. Now, this is interesting. It's still moving in increments, and it's not quite as regular as it was before. Watch that again. 600, 1,000, 1,600, 2,000. It's still incrementing in 400 milliseconds. So you see we're getting irregular behavior from this. If I made it 100 milliseconds, now it's in 500, multiples of 500. You have to remember that our scan time is not necessarily synchronous with our scan time stretcher. So you're going to see some irregular behavior in that timer data type. But again, we got into all this because we were using the greater than instruction to analyze our code. There's another thing going on here that you can't see. Even though you look at this and you see it incrementing in certain, look, see that odd value of 1, 2, 3, 4? Where is that coming from? Well, remember that the program is not synchronous with the IO update. Plus, you're looking at a screen. The screen has a refresh rate that is totally unsynchronous with the controller. So there's just a lot of things going on here that are misleading. You had to save your project and go offline.